welcome to module 2 lecture number 6, and this is on phasor estimation technique will and continue with the discrete Fourier transform. So, in this lecture we will learn a phasor estimation technique particularly on discrete Fourier transform, and however, this module includes different other phasor estimation techniques including least square technique and Kalman filter technique, and this is an important, you can say that topic in numerical laying algorithm perspective. Now, we know that a phasor represents for a sinusoidal quantity like you see here, this is a voltage signal sinusoidal quantity, and then these can be represented in terms of a phasor and anticlockwise rotating vector in the same speed you can say omega that of the sinusoidal quantity. So, this you can say that this vector represented by magnitude of A, and then you can say that its projection on y axis, and so we can say that represents for this sinusoidal quantity. Now, this is what we remember, you can say that use the sequence component. In the sequence component you are in need of VA, VB, BC, IA, IC to get the corresponding positive sequence, negative sequence and zero sequence components, which are being widely used in different relaying principles algorithms. So, essentially from a sinusoidal quantity we require different the corresponding phasors to be computed, and these phasors you can say that are very much required for the different computation process. Like one example, you can say that when we are talking about impedance in a distance relay, this impedance is a function of voltage and current phasors. So, these voltage and current phasors. So, phasors can be represented in a complex form, either polar form or rectangular form, and then you can find the corresponding impedance a complex number in this one. And in impedance relay we can use the Rx plane, and there you can say that the corresponding decision is being carried out by the relay, you can say that using that complex number. So, we see that you can say that most of the relays, available numerical relays, use the phasors for the decision making process. Now, for this perspective there are different the relays, different phasor estimation algorithms available, and as I mentioned, and we will start with the more very commonly applied technique one cycle DFT, and in the subsequently consider we will see also its how the corresponding DFT can be computed in a better way using recursive DFT. Also you can say that its variants in the form of half cycle DFT and the cosine filters, you can say that more you can say that efficient filter, you can say that extension of this concept, you can say that of the one cycle DFT will be, you can say that applying those techniques. Now, let us you can say that see this signal. So, this you can say that represented by as mentioned here about the this V t sine of omega t plus theta with omega the angular speed, and this you can say that let us say you can say that the corresponding sinusoidal signal. So, this voltage signal with plotted on the time axis, we get the corresponding signal to be like this. So, the objective you can say that how to extract the corresponding fundamental component, and that you can say that should be represented in the form of a phasor, and that phasor you can say that is being used by the relay algorithm. So, you see you can say that here this signal has to be, you can say that data aggregation system has to be accomplished through the A to D conversion process, and those samples you can say that will be used for the subsequent phasor estimation technique. So, let us you can say that we sample the signal like this. These are the different samples values in this process. So, these samples value we represent V n to the same signal V p sin omega t n plus theta. So, this t n you can say that is nothing but the corresponding n into delta t, where delta t is the interval between two successive points, consecutive points, that is the time interval between two consecutive points, and the n is the number of samples. So, as the one by one you can say that the relay possesses you can say that newer and newer samples, then the corresponding you can say that the n also goes on increasing one by one in this order, and that you can say that the corresponding time also on the time axis that goes on increasing. So, for this you can say that continuous sinusoidal waveform, these are the samples you can say that which are being acquired by the relay through the A to D process. So, after obtaining these samples, we like to consider use these samples for the phasor computation process. Here in this sampling perspective, we see considered here this is 8 samples per cycle, this is a 50 hertz signal, and so therefore, you can say that the delta t considered is 0.02 by 8 the interval time in that perspective. Now, see the consider that how the one cycle discrete Fourier transform algorithm is being applied for the phasor estimation process. So, this you can say that our the corresponding samples value being acquired by the relay as already mentioned, and then you can say that we will apply the corresponding phasor and say that one cycle DFT technique. The phasors which is being computed by this one cycle DFT process is the summation of you can say that from n equals to 0 to n minus 1, where capital N is the number of samples in a cycle, one cycle period in the 50 hertz system is 20 millisecond. So, in that 20 milliseconds how many number of samples are being acquired by the A to D process, that is what the capital N, and the V n you can say that here is the nth sample of the V t. So, that V t you can say that the V n you can say that nth sample of the V t. So, for the each V n we have a coefficients Fourier coefficients in the form of e to the power minus j 2 pi by n capital N into small n. So, this you can say that complex coefficient, complex weight to this individual V n is being multiplied, and the summation of you can say that for all the you can say that n number of capital N number of points gives us you can say that this part of these things, and then that is being multiplied you can say that root 2 by n. Typically, you see some literature you can say that you will find you can say that 2 by n factors, and because in power systems we use you can say that phasors mostly instead of the peak value. So, therefore, you can say that peak divided by root 2 gives you 1 by root 2. So, that root 2 factor is coming you can say that because of this RMS value being used in this perspective. So, therefore, we can compute you can say that the corresponding phasors using this you can say that the corresponding mathematical relations. So, once a fresh sample is being obtained by the A to D conversion process, the relay gets it and uses you can say that a set of you can say that sample value n number of points available to that, and then you can say that to the each value you can say it multiply its corresponding Fourier coefficients and find out the consider this one and the corresponding phasors. So, these being considered the complex number, the corresponding V dot becomes you can say that a complex number comes out to be in terms of that. So, what we see consider that from this relation is that to the each sample value the corresponding Fourier weight being multiplied, and then you can say that the relay for say that computes the corresponding phasor value. So, now we can say that for this complex number for the computational process we can make it easier also in the algorithm process, and the corresponding processing element may not be able to execute you can say that the complex number. So, what you see that if you segregate the corresponding real and imaginary part, the real part of this you can say that phasors this becomes equals to root 2 by n equals to 0 to n minus 1 b n, and the real part becomes cos 2 pi small n divided by capital N, and similarly the corresponding imaginary part becomes you can say that with a negative sign you can say that root 2 by n summation of you can say from n equals to 0 to n minus 1 and then b n sin 2 pi small n divided by n. So, this you can say that we divide the corresponding complex number you can say that to the real and imaginary part. You can call it, you can say that the cosine component part, and also you can say that the sine component part for the corresponding B dot phasor also. So, we can say that this B dot, that is the voltage phasor for the sinusoidal quantity which we are representing, can be, you can say that can be expressed in terms of B dot equals to V real minus j V imaginary, and that equals to V magnitude with an angle of theta, the polar form you can say that we are expressing for this case. So, we see clearly that from the voltage samples we can multiply the corresponding Fourier coefficients, and then you can say that we can get the corresponding B dot phasor, you can say that in terms of this, and which you can say that we can express in terms of a polar form, you can say that in terms of B with angle of theta, and where the corresponding magnitude becomes, you can say that is there nothing but this V real component and the corresponding V imaginary component, square of that, summation of that is magnitude, and the corresponding angle can be obtained, you can say that from the tan inverse, you can say that V imaginary by V real with a negative signs to take care of the corresponding negative part of the Fourier coefficient. So, this in overall you can say that gives us the corresponding phasors computation process, you can say that for this perspective. In overall you can say that we see that with samples value for the phasors for the signal being available for one cycle of, you can say that signal, we multiply the corresponding Fourier coefficients with the corresponding Fourier coefficients and find the summation of that one, multiply with the root 2 by n, that you can say that the corresponding processor now gets the corresponding voltage phasor for that particular window of signal. Now, we will see how we can say that this computational process is being accomplished through an example. Let us say consider that a signal, a sinusoidal signal V equals to 109.53, an example sine of 100 pi t plus 22.25 you can say that degree is the voltage signal, which is you can say that the corresponding processor you can say that acquires to the A to D process samples you can say that, and the samples are V n equals to 109.53 sine 100 pi t n plus 22.25 degree, and the sampling rate you can say that we have taken here is 0.4 kilohertz 400 hertz that is, and because this is you can say that 50 hertz signal. So, the number of points you can say that per cycle this is for each you can say that cycle we are getting you can say that a number of points to be n equals to 8 points. So, this is you can say that take simple you can say for the calculation process. However, a typical relay today you can say that can be taken you can say n equals to 64 or more or so you can say that for more you can say that accurate calculations and efficient calculation also for relation process. So, here you see here this is the voltage signal which you can say that we are getting, and these are the samples you can say that in this process, and these are the can say the time index you can say that of that corresponding T n, and then you can say that these are the corresponding V and sample value corresponding value sample value of the voltage of this one. So, we have a record from 0.1 here this value, and this is the corresponding 41.47 value, and like that you can say that we progress the relay acquires the data you can say that for the different time index and stores the corresponding voltage information one by one you can say in terms of that. Now, what you see you can say that we will learn you can say that from this example we see here. Now, this we require for the one cycle DFT you can say that one cycle of data you can say that for this one. So, this window you can say that provides us you can say that a data you can say that of one cycle. So, this is you can say that from 0.1 to you can say that to the one cycle data. So, it you can say that the corresponding one cycle data here you can say that are being 41.47 to the minus 42.37 you can say that sample value. Note that you can say that the next sample again comes out to be you can say that 41.47. So, we see here you can say this you can say that one set of data you can say that which you can say that which is nothing but the corresponding n equals to 8 in this case. So, these you can say that set of data are to be now processed by you can say that the one cycle DFT for computation of the phasors. So, similarly you can say that when we are going for you can say that another window you can say that next window progress you can say that in this case, then the a fresh sample is being acquired by the you can say that the relay, these fresh samples is being acquired by the relay. So, the now corresponding window ceased by one sample, it discards this sample and then progresses ahead. So, therefore, again you can say that in the second window you can say that we see it acquires the new samples and discards this sample, and then you can say that the second window you can say it is being the new fresh window comes out to be there, and then you can say that in this way you can say that this is a progressive window with a newer and newer samples being acquired by the relay. The corresponding window goes on shifting, and then the corresponding 1 cycle DFT computes the corresponding phasors using that the formula which we have already shown in the earlier slide. So, this you can say that called the moving window approach of you can say that computing the phasors. You can say that with every new samples the corresponding window is being updated and the relay computes the corresponding phasor for the further calculations. One point again I am telling here that once you can say that this sample is being acquired, the corresponding phasor is being computed, the relay then starts computing for further you can say that things like currents, voltage, all phasors, impedance and so, and thereby consider the relay the uses its principle in this in this you can say that interval, and this principle you can say that using that principle and the or the method you can say that the corresponding relay decides that whether to trip or not trip. So, when we consider the new fresh samples again comes, the relay you can say that by that time already has you can say that decided it is no you can say that then in case of fresh samples again it computes the phasor, and again you can say that goes for the processing of its you can say that algorithm inside this one. So, that is why in this interval of time you can say that the relay has to accomplish data acquisition and as well as you can say that to compute the phasors or so you can say that, and then the corresponding decisions to be there, and that you can say that is the typical relay performance that you achieve. So, therefore, if the relay or algorithm uses higher and higher sampling, then the interval you can say that which is available to the relay will be smaller and smaller, but the relay has to take decision within that smaller interval of time, and that becomes challenging, and therefore, it has associated cost, and that you can say that limits the you can say that in the design process, and that based on all these perspective and all these things the relay has to take the corresponding consider decision for a successful operation of the consider that the operation of you can say that the protection scheme and so. So, these you can say that the corresponding things. Now, let us you can say that see how you can say that we can compute the using the corresponding samples value using that 1 cycle DFT. See here you can say that these are the data sets which we have already mentioned in the earlier slide, and this is the corresponding time index for the perspective. So, the corresponding Fourier coefficient cos part and side part you can say that are being there, cos 2 pi by consider that 2 pi n by n. So, this corresponds to you can say that the corresponding cos weights, and this corresponds to your sine weights. The small n you can say that is corresponds to the sample number, and capital N is nothing but the in this case you can say that is 8, that is number of samples per cycle. So, if you put the substitute value of n equals to 0 to n minus 1, n equals to 0 means cos becomes 1 and sine becomes you can say that 0, and then you can say that cos n equals to 1, 2 pi 1 divided by 8. So, this gives you can say that a 45 degree. So, therefore, this becomes equals to 1 by 1 divided by 1 over 2. So, also for the sine weight, and like this you can say that you substitute the n equals to 0, 1, 2, 3, 4, 5, 6, 7, and then you can say that we are getting the all you can say that 8 weights you can say that corresponding 8 weights for the purpose, and this you can say that similarly you get the corresponding sine weights for the you can say that the corresponding sine weights we are getting in this perspective. Then in this case you can say that after you can say that we will multiply the corresponding weights to the consider to the samples values, and this you can say that sample values and the weights are being multiplied you can say that for the perspective, and like this for this perspective individually, and then you can say that to the individual sample value, like for example 41.47 into 1 that gives you can say that the corresponding 41.47, and 41.47 into 0 gives you 0, like this 101.04 into 1 by root 2 gives us 71.42, and so also 1 by root 2 this is 71.42. Like this you can say that the corresponding sample value and the corresponding cos and sine weights are being multiplied, and we are getting you can say that a set of you can say that values for the cos part and set of values for the sine part you can say that for this case, and this you can say that is being used you can say that in the next case. So, what you say that in the 1 cycle DFT you get the summation. So, summation of you can say that these you can say that sets you can say that gives us you can say that 165.88, and summation of this part you can say that gives us you can say that 104.58. Now, using the corresponding algorithm you can say that we get the corresponding now voltage phasors V dot for this case for this 1 cycle of data using the 1 cycle DFT is root 2 by n, capital N is any 8 here, this 160.100 sorry this corresponding 65.88, and with a negative sign you can say that 405.48 this, and this gives you can say that the corresponding phasor value to be, you can say that 77.45 magnitude, angle of minus 67.75. And note that this is for the particular window of data which we have taken these 8 samples value, and the corresponding phasors you can say that gives you this one. Now, with a fresh samples, this window will be again updated as I already mentioned, and then you can say that we can get a corresponding phasors value to be the corresponding phasors value to be considered a different value. And then you can say that like this you can say that the corresponding signal progresses, and the relay acquires you can say that newer and newer samples, and accordingly you can say that the corresponding phasor is being computed, and then you can say that fresh sample you can say that phasor is being used by the relay for decision making process. So, now you can say that in the second window you can say that what you have already mentioned, in a fresh sample is being acquired, and this fresh sample you can say that is being used by the relay, and it discards you can say that the older sample, and this is a new set of data you can say that for the second window. So, using this window again you multiply the corresponding cos and sin parts and get the corresponding values you can say that like this, and then you can say that using this you can say that cos and sin weights we get the corresponding set of you can say that these values, and then when we add the you can say that the real part or the cos part in this case we got this corresponding value to be you can say that 404.02, and you can say that the corresponding you can say that the sin part you can say that summation gives you 169.44. Therefore, the corresponding you can say that phasor value in this case becomes you can say that in the second window this becomes root 2 by n, that is capital 8, and then you can say that this real part you can say that real part of you can say that this gives us you can say that to be 404 point this, and the imaginary part becomes 169.44. So, this at these situations the corresponding phasor you can say that computed becomes 77.45 magnitude, and with an angle of minus 22.75 you can say that degree. So, this what you see you can say that from the now you can say that with the second set of window we again you can say that in a similar we can say that computed the different the weights and corresponding multiplication of the different weights and get the summation, and then you can say that we get the corresponding phasors you can say that to be computed you can say that for the second window. So, what we see you can say that from these two windows you can say that the corresponding things. So, for first window the blue one, and then you can say that the second window the green one. So, with the new sample the second window is being say that updated accordingly. Now, if you see these computations and phasor and you plot in the you can say that in a polar plot like this with the corresponding phasors you can say that rotating in anticlockwise direction with the same speed as omega speed that of the sinusoidal quantity. So, the first you can say that the window gives us you can say that the blue you can say that blue phasors that you can say that magnitude and you can say that angle we have already mentioned, and the second window you can say that gives us you can say that the corresponding magnitude and angle like this. What we see you can say that from these two you can say that the corresponding magnitude you can say that remains same, but the angle you can say that has in both the cases are you can say that the angles are being different. Now, what is the difference you can say that we will notice here you can say that we will see here that the magnitude of both the phasors are same, but the angle you can say that here becomes you can say that 45 degree in this case. What is that 45 degree between window 1 and window 2? If you see here you can say that for this case the corresponding delta t between you can say that these two windows, the window 2 shifts by an angle time of delta t. What the delta t talks about? It is nothing but the corresponding 0.02 by 8 you can say that samples, that is n 8 corresponds to that capital N value, and this you can say that is nothing but one cycle 360 degree divided by each sample interval divided by 8, that gives us 45 degree. So, this delta t you can say that corresponds to you can say that in this case corresponds to this 45 degree perspective for this you can say that things. So, therefore, that 45 degree shifting of you can say that window 2 in the time you can say that domain is being clearly reflected in the phasor computations domain, and that is you can say the reason we are getting this shifting of angle of 45 degree by this one. Note that you can say that the magnitude of this signal you can say that remains stationary. So, therefore, you can say that the corresponding magnitude part you can say that remains to be same in the both the cases and so. So, this you can say that clearly shows that this one cycle DFT is able to capture the you can say that phase information and both the you can say that the magnitude information. Note that the 77.45 is nothing but the corresponding signal, you can say that you talk about signal divided by root 2. So, that is exactly you can say that as 77.45 magnitude you can say that thing. Now, what you see you can say that from this perspective is that with further and further window shift you can say that the corresponding phasors can be computed in the proper way. Now, let us you can say that see how good you can say this corresponding one cycle DFT in filtering out the different unwanted component. Like in this example, we have taken you can say that a signal, you can say that this signal you can say that is contaminated by different harmonic components, and like you can say that same sinusoidal signal we consider you can say that that again you can say that 109.5 so that 53 sin 100 pi t you can say that with an angle of minus 20 with this same signal we had taken, for which we computed the phasor to be considered with a magnitude of 77.45 and with certain angle depending upon the different windows, and we add you can say that now you can say that this the second harmonic component 200 now instead of 100, this is 300 now, third harmonic component, and then we have also fifth harmonic component you can say that for this one of different magnitude. Fifth harmonic component 10.95 this is, and then you can say that 16.43 and you can say that 5.03 different percentage of you can say that second, third and fifth harmonic are being added to this one. Now, this signal is now highly distorted you can say that from the fundamental, which is clearly visible you can say that from this you can say that plot of the signal. Now, you see you can say that this signal you can say that the data to be data acquisition is to be accomplished by the A to D process, and then you can say that again we are maintaining the same 400 Hz sampling rate with the capital N you can say that for the 50 Hz signal being you can say that maintaining to you can say that to the n equals to 8. Now, consider this window. In this window you can say that we have 8 number of samples. So, this 8 number of samples it corresponds to, and then you can say that therefore, you can say that the corresponding window becomes like this. So, this you can say that this window refers to this you can say that window of you can say that signal. So, we have you can say that these you can say that samples you can say that are to be say that process, and the corresponding one cycle DFT you can say that is to be used for this perspective and all these things. So, how the corresponding one cycle DFT finds the corresponding this signal you can say that for this case you can say that we will try to you can say that evaluate using the same you can say that calculation process as we have already mentioned you can say that earlier also. So, if you see that you can say that the calculation reveals that you can say that for that window, if you again you can say that applied the corresponding you can say that things to be similar we can say that, then we see here you can say that for the same you can say that one cycle of you can say that data, that window which we have mentioned for this period you can say that the corresponding value of you can say that real part becomes this and the imaginary part comes out to be 405.49. If you see the you can say that two components, it is we have already seen these two components earlier also, and if you put the in the phasor form you can say that like this for the corresponding component, the phasor V dot you can say that comes out to be 77.45 magnitude, which is same as what we earlier also get, and angle of minus 67 point you can say that 75 degree, which is exactly same you can say that for the case you can say that which you got earlier case also. So, what we see here is that the corresponding earlier calculation of you can say that without harmonics we got the corresponding you can say that the corresponding you can say that in the first window in earlier also 77.45 with an angle of minus 67.45. So, these two you can say that values are you can say that exactly same. This clearly shows that the different harmonic components second, third and fifth are completely being rejected you can say that by the one cycle DFT, and that is what we want in a relay also, that because if the phasors is to be used by the consider that by the relay, the phasors should be considered as accurately as should be estimated in the from the signal for successful operation consider that and accurate operation, accurate decision by the corresponding relay in the system. Now, we see here you can say that how these phasors you can say that as you have already mentioned you can say that are being useful you can say that in the relay decision placing to have you can say that picture on that. This you can say that take sinusoidal signals voltage and current. So, blue one is voltage and the red one is current perspective in this case for example. Now, you see here you can say that we select an window, and in this window you can say that you compute the corresponding phasors for both voltage and current. So, we can get the corresponding voltage phasor and the corresponding current phasor in polar form or in rectangular form with V for a particular instant with an angle of theta 1, and the corresponding current for this case let us calculate by the 1 cycle DFT is I with an angle of theta 2. So, clearly you can say that for this case we can find the corresponding angle between voltage and current phasors. Theta 1 minus theta 2 you can say that is indicative of the what is the corresponding theta value. So, this phase information is very important, you can say that in relay applications like directional relaying and in many other you can say that application perspective, including the magnitude part also you can say that use both voltage and magnitude and angle are being used in distance relay application and so. Now, come to you can say that another one, this you can say that take one cycle DFT, how one cycle DFT can be useful you can say that in this sequence component perspective. Let us say here you can say that these three you can say that plots are for voltages you can say that in a system A, B, C. So, you can say that we have these are the three you can say that voltage you can say that signals, and we like to use you can say that how to compute the corresponding. So, the each you can say that signal will be using the one cycle DFT you can compute the corresponding phasors. Let us say at one window you can say that we will take, and this window of you can say that length, in this window you can say that we will take a number of samples and capital N, and then you can say that for each phasor you can say for each signal you can say that we will take the compute the corresponding phasors V A, V B, B C with the angle theta A, theta B, theta C are the nothing but obtained phasors using the one cycle DFT for this window. Then using the transformation, as you have already learned that we can compute the V 1, V 2 and V 0 the sequence positive sequence, negative sequence and 0 sequence component corresponding things for the purpose, and these sequence components you can say that as you know are being very you can say that widely used for you can say that in different numerical relays you can say that for decision making process. So, this you can say that with you can say the window progressing the corresponding V A, V B, V C will be also estimated using the one cycle DFT, and the corresponding sequence component will be also updated accordingly. So, what you learn from this is that from a you can say that for a different you can say that current and voltage signals using the one cycle DFT algorithm which uses the different samples value and the corresponding Fourier coefficients, it you can estimate the corresponding fundamental component using that phasor estimation principle very efficiently and thereby can say that which can be used for the consider relay decision making process. So, in the next class we will see how you can say that other you can say that variants of the one cycle DFT algorithms can be also used for phasor estimation either better way for the relay decision making process. Thank you.